Hello guys, how's it going? This is Mike coming back at you here with another video on number theory. In the previous video, we saw several sample problems where we reverse engineer the Euclidean algorithm to come up with those specific integers that allow us to write our GCD as a linear combination. We said that that process of reverse engineering is going to be used in the next section, so we have arrived at that section. In this section, to wrap up Chapter 2, we're going to talk about the linear Diophantine equation. When do we have a particular type of solution? Can we find all solutions? And then how do we find those particular solutions? So as I just mentioned, we're going to look at linear Diophantine equations. And these are equations of the form ax plus by is equal to c, where a, b, and c are all whole numbers. Now, ax plus by is equal to c here looks like and is the general form for a linear equation. However, what we are interested in for the purposes of number theory is when does this equation have integer solutions? When do we have values of x and y that are whole numbers that will make this equation true? We have numerous, in fact, infinitely many cases out there where an equation of this form, if we have whole numbers substituted in for a, b, and c, we have infinitely many cases where there are no integer values for x and y that will make that true. So we want to know, when does this type of equation have integer solutions for x and y? We need to look at under what conditions do we know that we have integer solutions. And then once we know that we can find integer solutions, do we then have a formula or a set of formulas that we can use to find all integer solutions to a given linear Diophantine equation? So that's what we're going to do in this video. We're going to talk about those conditions. We're going to talk about the formula that gets us all integer solutions, and we're going to see a run-through of one problem. In the next video, we'll go through more sample problems to get ourselves more accustomed and more used to the method that we're going through here. So first, under what condition do we know that a linear Diophantine equation has integer solutions for x and y? The linear Diophantine equation, again in the form ax plus by is equal to c, has integer solutions if and only if d, which is the GCD of a and b, divides c. So you take the GCD of a and b, you figure out, does that GCD divide C? If it does, then your linear Diophantine equation does have integer solutions. If the GCD does not, then you would say the linear Diophantine equation does not have integer solutions, and then you would stop right there. Because for our purposes, we're only concerned about integer solutions for x and y. So once you've verified that your equation does indeed have integer solutions, and once you found a particular solution, once you found one x value and one y value that satisfies your given equation, how we do that we'll see very shortly. You can then come up with all other solutions. And there's a separate equation for the x's and a separate equation for the y's. Any x value is of the form x naught, the one x value that you found, plus b over d. Again, d is the GCD of a and b. so b over d times t, and y is equal to y naught, your specific y value that you found, minus the quantity a over d times t. And t is an arbitrary whole number. So how this would work is, once you've set these things up, once you've plugged in your x naught, your y naught, your a, your b, and your d, what you would do is you would take an arbitrary whole number, you plug it into each equation at the same time, and the x value and the y value that you get, those two guys satisfy your linear Diophantine equation. You don't plug different t values in to each of the two e equations. Those won't necessarily work. So how do we find one particular solution to then get all possible solutions to a linear Diophantine equation? We're going to do the exact same thing as what we did in our previous video. We're going to find a way to write the GCD of A and B as a linear combination of A and B. We're going to find those whole numbers x and y, but then we're just going to add one little step onto the end of that. So this is the one example that we'll see in this video. In the next video, we will do more sample problems to see how this all makes sense. So we're going to find all solutions to the Diophantine equation 54x plus 21y is equal to 906. Now, first thing you always have to do is find the GCD of your A value, and your B value, and make sure that that GCD does indeed divide your C value of, in this case, 906. It's not too hard, not too bad to find out that the GCD of 54 and 21 is 3, and 3 does indeed divide 906. So we know that there are integer solutions to this particular linear Diophantine equation. Now we just have to find them. And we have to start off by finding one of them. We are going to use the Euclidean algorithm there, not the division, but we're going to use the Euclidean algorithm on our A and B values of 54 and 21 to see, to find the GCD, and then we're going to reverse engineer that process. So going through Euclidean algorithm, 54, you can get two 21s out of that, and you have 12 left over. Once again, 21 becomes your new A value. So B becomes new A, R becomes new B. You can get 112 out of 21 and have 9 left over. You can then get 9 out of 12 and have 3 left over, and then you can pull exactly 3 3s out of 9, and you have 0 left over. Now we're going to reverse engineer those steps. So write your column off to the side here. 3 is 1 times 12 minus 1 times 9. 9 equals 1 times 21 minus 1 times 12. And then 12 is equal to 1 times 54 minus 2 times 21. And just like we did in our previous video, we're going to start with the bottommost row in this right-hand column. We're going to then make substitutions. Work with the next line up, substitute in, combine like terms, regroup, whatever, and then go next row up, substitute that, result in all that good stuff. So 3 is the 1 times the 12 minus the 1 times the 9. Substitute in for the 9 like we had here. Right there, that's going in here. Combining like terms, I have -1 21s and plus 2 12s. I'm now substituting in for that 12. That's going to go in right here. And when you multiply things, combine like things, you get -5 times 21 plus 2 times 54. Now, again, just noting what things are where, it's 54x plus 21y. So this guy, so this number here, when we're all said and done, is going to be my x value, and then this guy here, again, when we're all said and done, is going to be what my y value is. Those are not the actual x and y values. This is where that one more step comes in. So what we did here was we found two whole numbers such that I can write the linear combination of 54 and 21 as the GCD. But what we want to solve in our equation is we want to find the particular x and y values that make 54 times x plus 21y equal to 906, not necessarily our GCD. So what we have to do is we have to take the 2 times the 54 minus 5 times 21 that we currently have equal to 3, and we need to multiply each side by the same number so that we get something involving a 54 and a 21, and a combination of those equal to 906. So basically, we need to fill in each of those blanks. So to go from 3 to 906, we multiply by 302. What we do to one side, we have to do to the other side to make sure that it stays the same. So I'm going to multiply the right-hand side by 302 as well. But when we multiply by this 302, we're only going to multiply that 302 into the number out front. Just like in the previous video when we learned about reverse engineering the Euclidean algorithm, we said that we only multiplied the numbers out front by that coefficient. Well, we're doing the same kind of thing here. So that 302 gets multiplied into the -5, and it also gets multiplied into the +2. So I have 54 times now 604 plus 21 times 302 times -5 is -1510. So we have 54 times some whole number plus 21 times some whole number equal to my 906. So this 604 and that -1510, that is my particular solution. This is my x naught, and this guy right here is my y naught. These are the guys that we're going to use in the formula to come up with all integer solutions to this particular linear Diophantine equation. So, as I just said, we have thus found a particular solution, x naught 604, y naught -1510. We can now find every possible integer solution. If we go back to our formulas here, we know our x naught, we know our y naught, we're given a and b in the problem, and we figured out what our GCD was. It was 3. So we make these substitutions in, And we come up with the general formula for all integer solutions. X is 604 plus, it was B over D. Our B value is 21. Our GCD was 3. So we have 604 plus 7t. And then it's y equals y naught, the negative 1,510. And now it's minus a over d. A was 54. GCD was 3. So we have 54 over 3, or 18. So that gives us negative 1,510 minus 18 t. And for each of these guys, t is an arbitrary whole number. So what we can do now is we can take any whole number whatsoever, we can plug it into these formulas, again plugging the same t value into each of these formulas, and it will give us another integer solution to this Diophantine equation. For example, if t was equal to 1, then your solution, xy, is equal to 611 and then negative 1,528. If t was equal to negative 2, we would have 604 minus 14, which is 590. So that's the x value. And then we would have negative 1,510 plus 36, which is negative 1,474. So that's just how you would come up with more integer solutions to this particular linear Diophantine equation. Take any t value, plug it in, you come up with another solution. So this was our sort of brief get our feet wet with solving linear Diophantine equations. When can we solve them? If we can solve them, how do we find all integer solutions? And then what's the process that we have to go through? Again, the process is everything that we did last video, but then one more multiplication added on at the end. As I said, in the next video, we're going to do a few more sample problems here. We're going to get more practice with solving these types of equations. If you have any questions or comments, please be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.